So welcome back, everyone. So our next speaker is Pedram Roushan from Google Quantum AI, California, and he'll be talking about quantum simulations with superconducting qubits.
Yeah, so good. Yeah, thank you. Thanks. I'd like to start by thanking the organizers for inviting me, and I'd like to thank all of you for giving this talk a chance. So let's see, hopefully we make it interesting. This is the first experimental talk as far as I could tell in this workshop. So maybe, let me tell you a little about the hardware, and then I talk about two of our recent experiments. So you know how the hardware looks like, and then maybe shows that I'm an experimentalist, so you don't ask very hard questions. That's also part of it. So the working horse of our platform, of our quantum processor, is superconducting Josephson junctions, which is simply two islands of superconducting placed very close to each other, so close that Cooper pair can coherently tunnel. In reality, they are, this is the pointer, or is there a laser separate? If you have a laser pointer, okay, this one. Oh, good, okay. So if you deposit a layer of aluminum and then you oxidize the chamber, maybe get 5 nanometer of aluminum and deposit another layer of aluminum, you're realizing a Josephson junction, which can describe by Josephson relation, which every superconducting island can be described by a complex order parameter, which has amplitude and phase. If these two phases are different from each other, then you get a coherent tunnel, then you can get a Josephson current, and if this phase relation is changing with time, you get a Josephson voltage. And it's very simple to show that this forms a nonlinear resonator, meaning that you have an inductor, which is inductance is depend on the phase difference across the two junctions. So that's a key element because it allows you to make cosine potentials. Nonlinearity leads to a LC oscillator, which is not parabolic, but it's cosine potential. And that's a very significant difference because now the level of spacing is non-uniform, and now you can address different layer levels in this potential. And in reality, you, okay, now I have to remember. Ooh, went so far. Now I have to remember. Now you can put it in these junctions, you can make two of them for some technical reasons, and then you can put it next to a capacitor, form a resonator, which we can control its resonance frequency. What we do is we put an array of them together. Here you can see it's a 1×9 array. Later on, we went to 2D, but that was done in Google, so I cannot show you the picture. This is the latest I could show. It's a decade old, but conveys the message that so you have Joseph here. You can see that we are giving them some color, so you see the functionality. Each of these capacitors are colored red, and then there's a Josephson junction followed by it, and then between each two qubits there is another qubit or another nonlinear resonator, which you can tune its frequency again, and you can realize hopping between two qubits by virtual hopping to these coupler elements. And on top of the qubits, you see a meandering line, which is a linear resonator, and the start shift down to qubits on those resonators will give you the occupancy of the qubits, so you can read the states of all the qubits at the same time by looking at the resonance frequency of the of the resonators and how much they're shifted from their frequency. But you can see that we have also lots of wire comes to the chip, so we control every qubit's degree of freedom. To move in a block sphere, you need two control knobs to control theta and phi. And then there's other knobs that go to the coupler in between to control the coupling strength between the two qubits. Could be anything between 0 and maybe 30 megahertz or so. Maybe that was too much experimental detail. Back to your familiar Hamiltonian language, we realize a Bose-Hubbard Hamiltonian at the end of the day. That means that you excite a qubit or two of them, and you come back and look at them later on where they have gone, what happened. They follow this Bose-Hubbard Hamiltonian with the nonlinearity of the qubits leading to the attractive Hubbard U potential. And you can see the range of the parameters and whatnot. But usually we don't go to the Bose-Hubbard limit. We are usually pulsing these qubits such that we realize 2-qubit unitaries and whatnot. So we have better control over them, and we can talk in terms of fidelities and whatnot. So yes. Couplers are another qubits which are at higher frequency. Qubits, you park them maybe at 6 gigahertz. These couplers are usually at 14 gigahertz, but when you bring them at 8 gigahertz or so, these 2 qubits, which are at 6 gigahertz, can have virtual hopping to that. And you write an effective Hamiltonian or reduced Hamiltonian for these two, it gives you this J-IJ coupling that I write. This comes as a result of me taking these couplers out of the picture. That's very common. So what are these systems good for? I will try to explain to you 2 recent experiments we have done. These kind of don't need any background in the subject. So hopefully you can all follow this. Physics is rather straightforward. And then you can see the degree of usefulness or the degree of computation that these qubits are capable to offer at these days. So they're not, well, maybe it's a spoiler, they're not going to cure cancer or fix Alzheimer for you in the next few months or so at least. That's what they can do, okay? Stay patient with them, and I'm about to explain what this experiment is. The first experiment is about integrability and breaking integrability in the Heisenberg model, or rather XXZ model. This has been studied where the beta ansatz integrability has started with this, so it's a century-years-old problem, and has been studied in the cold atom systems. Basically, there was a theoretical work that shows that this model have a bound state, and then it was realized in the group of Emmanuel Bloch that if you create magnons and these magnons stay together, meaning that you flip 2 spins in the middle of this chain, and you come back and look at it later on, and you see always they are traveling together. They form a bound pair, and they are traveling together. Okay, that's the physics, and this is the experimental cold atom data, and we're going to do a little cheating, and we're just going to pick up the same problem. Okay, slight difference. The slight difference is this. We are not going to do the Hamiltonian physics. We are going to do the Floquet version of it. For the Floquet version of it, there is a prediction from, there is a theoretical work from the Ljubljana group that are showing that this is also integrable. Okay, so let me say, if you take these Floquet steps, these unitaries to very small theta and phi, you realize the Hamiltonian. But if you don't go small, then you have the Floquet version of the Hamiltonian, Floquet dynamics. That's also integrable, and there is a work from our team, Igor Aliner, who shows that that also has a bound state. So that's the starting point for this experiment. Why this is interesting? It's interesting because the protection of the states come from integrability. You have an exciton in the middle of a semiconductor gap that is protected because there is nothing for it to decay to. But what I'm talking in here is something is stable because it doesn't overlap with the continuum. But we are going to have states which are stable and don't decay to continuum, yet energetically they are overlap with the continuum. So here is the Floquet version of it pictorially I'm representing. So we will see about that. Okay, so in a chain of 24 qubits, I have a grid of qubits. I can find 24 of them to form a closed loop by turning off all the other qubits in the gray. We are going to apply this unitary evolution. This is the every 2 qubit operation follows this 4x4 matrix, and we are going to excite few qubits and say, where did the excitation go? Okay, very simple question. And the color shows where the excitation go. First, we're going to go fully non-interacting. We put 1 photon, 1 excitation, 0, 0, 0, 1, 0, 0, 0. And we say, where did it go? We take a snapshot of it 10,000 times. It takes a second. And then you go to the next time slot, you look at the entire chain, and that's the picture you got. A very nice interference pattern of a non-interacting single particle, a catwalking or whatever it's called, I forgot. It's not catwalking probably. Anyways, then you put two excitations and you say, where did they go? And then you again take a snapshot and you see this pattern. It seems that they propagated slowly, but also it seems sometimes they break and go with the same velocity. And you put 3, 4, 5 particles next to each other, 5 excitations next to each other. And then you can see that there is a concentration of color, right? It's getting darker and darker. It seems they like each other and they don't get away from each other. That's interesting, but let me analyze this data a little further and more clearly. Let me just post-select on the cases that they are together, right? They say from all the bit strings I got, I can categorize into 2 categories. The case that they are together, we call them T. The case that they got divorced and one of them moved away. So we call them S. Let's just look at these ones, right? When you look at these ones, and well, they are together, so I can show you with the center of the mass where they are, right? And you can see the 2 excitation case now represented with a single pixel, with 2 of them are with a single color. It shows exactly the same pattern as the single one, except it's just slower. Meaning that the 2 are happily moving together as if there was a single particle in here with just a different velocity. And the same concept repeats itself for 3, 4, and 5. So you go all the 5, it gets extremely slower, but propagation got slower, but the concept of being together is there. So when you put them together, they don't go anywhere. And it's very interesting because as you can see, the number of, the size in the Hilbert space is really shrinking. It's linear in the, well, the exponentially large Hilbert space is in the cases of that they are not together. So there are n states, such states in a chain of n, and yet these manage to move this part of this Hilbert space without getting bothered to go anywhere else. This is consistent with the numerical prediction. Yes. Yes, 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 yes.
So where is the driving in this case? Because
driving is the, so you put qubits, you excite them, right? 5 of them, let's say, next to each other. And then these objects, this object is this unitary. You apply this unitary over and over again.
So does this mimic the XXG, the G part of the interaction?
In the, yes, I even highlighted the things. So there is a XXYY comes from this theta, more or less maps to theta. And then there is a ZZ delta, which maps to phi. Trust me on this, huh? Maybe.
So they like interaction in the nearest neighbor.
However, XXE is, yes. Hopping and interaction. Look, you're going to get even synthetic magnetic field. Believe me in this, then you're going to get a heart attack. Okay, so it follows the theory and it's all good. You good? Okay. Okay, so I want to entertain you guys with our version of the RPES measurement. You guys coming from solid state training and background, and you want to show you, if we want to show you a picture, the same physics in the momentum space, how far we can go. So I need to talk a little elementary physics, which hopefully familiar with you, but I want to show you, if you want to look at the same dynamic in momentum space, how far we can go. So let me tell you something which is rather probably very familiar to you, and that is, well, if you have a, so for now, we're going to switch to Hamiltonian for a few minutes. So if you have to explain this physics, so if you have a Hamiltonian, it has an eigenstate, and if you evolve under initial state, well, you consider initial state as this decomposition, of course, in the eigenstate energy of the problem. But if you evolve the system, sorry, how do I? Okay, so right, there is an initial state, and that's the evolution. Look at this overlap. Look at, if you could manage to compute this overlap, right, you would get this complex signal, which your Fourier transform gives you exactly the eigenenergy of the problem, right? Now the challenge is how to realize this overlap in the lab, right? It is just simple to write. It's overlap of a wave function with initial wave function. Let me give you a simple example. Let's say you have 4 qubits and you put 1 qubit on the equator and then evolve it under some unitary, which is particle number conserving. And then you manage to measure these non-Hermitian operator at the end of that thing. You may, this is not something you can measure in one shot. You have to measure X and Y and you put it together. And that expectation value of these operator is exactly that overlap that we were asking for. This concept can be going up to more and more qubits. It's not scalable. The operator that you need to measure grows exponentially in the number of particles. But nevertheless, you can construct it. You want to measure this lowering operator, you decompose it to 4 distinct things you can measure, and then you add them up. And then this physics just keeps going. So we can use this technique, which is not scalable, but we can do our momentum resolve, and you can get the band structure of the system by doing that. So let me show you how it looks like. So when you measure these lower operators, it looks like nothing. They look like garbage in time and space. But the 2D Fourier transform gives you the picture in momentum and energy, which is very similar to the picture you have in mind from tight binding physics. You can see the band formed by these 2 bound states. And we can continue on this physics going all the way to resolving the bands, which long behold, it follows the analytical relation that published in the Igor Aligner's paper. And from there, you can extract the effective mass of the band, I guess. You can okay, now you come that the degree of the freedom that exist in this unitary evolution is that we can also apply synthetic gauge field. So now the hopping in this can have a complex value. And the sum of these hopping is a synthetic gauge field that you can tune by simply, some of these beta hoppings is the flux that goes through the loop. So you can really get this band move as if you're penetrating a magnetic field through it. And you can measure the charge of these quasi-particles that we are creating. The final result is rather boring. You get the band to move and shift and see how much it shifts as I put flux in it. But the final result is rather boring. You put 4 or 5 photons, the quasi pseudo charge is 5 and 4. So it's not very exciting, but I want to show you the capability that we can get this band to move, a slide right in front of your eyes. Okay, so we're going to get a little naughty with our theories. So this whole thing was based on integrability, but integrability, as was mentioned yesterday, is a very fine-tuned concept. So you give it to an experimentalist, it's harder to respect it, but it's much easier to break it. Meaning that everywhere in this Achilles body is just non-integrable, and very easily you really have to really target hard to get to an integrable point. So you tell that to an experimentalist, they want to break the integrability right away. And of course, our role model and guru also very highly encouraged us to do that, so we cannot ignore him. The way we're going to break integrability is we are going to couple qubits to external qubit to a quasi 2 dimension. Basically, every other qubit, we're going to couple it to a qubit outside the chain. So we're going to go quasi 2D, and that breaks the integrability. The Hilbert space in this particular case goes by factor of 4, gets bigger. So after every 2 gates, we are going to have a new gate, which this gate takes us out of the 1D ring. If you ask any self-respecting theorist what's going to happen, they're going to use Fermi golden rule, and they say, oh, this goes away right away. This bound state is going to go to thin air in no time. Okay, so they would write you and educate you in this Fermi golden rule. Well, it happens, yes and no. So let me show you here.
Actually, I'm not able to follow this. So one thing is that qubits are highly anharmonic, I guess, and can we consider them as 2 levels?
Yeah, so right, that's a good question. With the pulse shaping that we did, we realized that unitary loyally up to 9999%. Okay, so 3 nines, we can realize the unitary, meaning that that nonlinearity is somehow important, but don't worry about that. Our job is to stay confined in 0-1 subspace.
Yes. So now that means also you should have strong on-site nonlinearity, on-site interaction.
adopt one picture. No, you keep, when you got in here, you got in here. Don't worry how we got in here. We are working in this 00011011. Don't worry how we got there. We got there. We're going to stay in this subspace with 3.9 fidelity. Yeah, we don't need to get worried about other physics. Okay, so the vertical axis here is like if the bound states stay together or not as a function of time. So if we were together, this line would have been flat, no breaking of the bound state. And this is, so this when there's no perturbation, they are together, but there's some dephasing induced decay. But when you make a very strong perturbation, that's a coupling to the external thing, you are going to see them quickly come down and break. What is interesting is this intermediate size perturbation, which could be as strong as the dynamic in the chain, yet the bound states are not broken. So let me show you more data and then maybe even a cut through it. So now the horizontal axis is the strength of perturbation. To perturbation which are very sizable, the bound state or stay together, this is just 2 cuts into this data. And then they break down. So they are not coming down very quickly. They have a very robust resilience to this perturbation, to this integrability breaking perturbation. I can show you the same picture in momentum space. That's what I talk about, momentum space. And the same physics follows. As you make the perturbation stronger, the bands of them disappeared eventually. But the rate that this band disappear is very flat initially, meaning that they are extremely resilient to this perturbation, integrability breaking perturbation. So, so that defeats the picture that we have in mind that goes with Fermi golden rule. And we pose that as a puzzle. And here is my claim to fame, that without us encouraging researchers to work on it, 2 groups picked up this problem. And maybe about a year later, they post their articles almost back to back on arXiv and try to explain this physics. One first group numerically confirmed our findings and took it to the limit, see how they are robust and whatnot. The other group is also try to explain it, and they say, well, it's probably a physics of the few body problem and goes away. But the most beautiful thing is that they don't disagree. There are parts that they disagree with each other, which is absolutely great. So this is what NISQ processors do, get very decent theorists entertained. That's the extent of the physics these processors do. Okay, we can talk about what they find if you want. So let me go to the second physics, and I want to talk about KPZ and the conjecture that we study about this classical stochastic equation and its relation to a dynamic in a 1D magnetic chain against. KPZ has been written maybe in 1986 to describe the growth of interfaces, how the interfaces growth. Is the simplest possibly modification to the diffusion equation. There is a diffusion term, and there is a simplest nonlinearity you can write, and then there is the last term is the noise in it. But since this lambda is positive, is a bit kind of difficult to solve it. So there is a conjecture, which we don't going to get into it, that is make it comfortable to deal with it, meaning that this ballistic deposition says that the universality class that you get out of this equation is the same thing that you get in this Tetris game. So the particles come, and if they see something in the left or the right, as soon as they see it, they get stuck. So you can take a snapshot of it, and you can analyze the height. There is a correlation length, and there is a fluctuation in height. And that's what we can, for that, there's a universality that falls into the KPZ universality class. And that is what we are trying to connect to our magnetic chain. So the equation describes phenomena that we see around ourselves, how this front grows and, the fluctuation whatnot on this growth of a fire or stains of coffee stains. But it has been conjectured that the spin dynamics in 1D Heisenberg chains also follows it let me be a little more specific. So there is this height profile. If you take the derivative of this height with respect to space, the counterpart of it in the Heisenberg chain is the magnetization profile in a chain. And if you integrate them, this height at a given place in time and space minus the asymptotic value, this relative height at the center, is its scales similar to magnetization, transferred magnetization, which is the number of excitation pass through the origin. So let me just give you pictorially what it means. Because there's yet another parameter which becomes significant in the talk. If you deposit, if a snow deposit on a flat surface, flat ceiling, you measure the height at the center, subtract the asymptotic value. That means that this initial parameter mu was 0. There's one universality class for it. And if the snow is deposited on some slope ceiling, either up or down, there's a different universality class for it. And we're going to check them both systematically. But anyways, this height, as it gets formed, it's exactly the dynamic of it is analogous to this transferred magnetization. So what we're going to do, well, okay, so where does this whole idea come from? Probably we can blame Marco on that. So it comes from this extensive numerical study, which goes order of magnitude to study the, what do you call it, scaling function. A scaling function has been measured very precisely for this equation, and numerically it's been shown that it deviates from Gaussian and is very close to KPZ. That's led to the conjecture that dynamics fall into the KPZ universality class. So it's a very sophisticated numerical techniques, and you see orders of magnitude. Okay, so this is what we're going to do in the lab. We're going to get 46 qubits, and with the probability of e to the mu over that normalization, we're going to excite the qubits on the left, and we are going to make the ones on the right to spin down. Okay, so with the so it's not a sharp domain wall. You know, there's a probability. This mu is a positive number, maybe 1, maybe 5, maybe fraction of fraction close to 0, but it's a positive number. And that's a probability to have blue on the one side and probability of having yellow on the others. And you're going to make this, and you know, you're going to put someone to count how many excitation has crossed the middle line. At the qubit 23, how many blue crossed the boundary. And you measure it as a function of time over and over again, and you form a histogram. As you see, we are losing excitation, so you can post-select on it. So you can see it on a normalized and on absolute scale. And we are going to analyze these histograms to death next. This is what you get. These are some of the typical observations, measurements that we have. Let's say mu is infinity. Now everything on one side is blue initially, everything on the other side is yellow initially. And that's one instance of it. And then I'm showing you instances that we collected, but at every time a step, we could collect up to millions of a step in a matter of minutes. And then you are going to go lower in mu, and you can lose the contrast initially, but again, you get data. Maybe worth emphasizing that this conjecture, here is the challenge in this to verify this conjecture. This value of mu, this initial domain wall contrast, has to go to 0, which means that, yes, it's, really it's easy to analyze this one because it has a sharp contrast, but that's not the point. The point is to come and analyze this one, which has a very low contrast. That's what the conjecture is about. So anyways, after you got these, you form a histograms, and I'm about to show you analyze the moments of these probability distributions. So first, we look at the variance and mean and variance of these probability distribution. That's rather straightforward in a sense that it has been done to death by many other people, and there is not much to be worried about in here. For this value of delta, if you remember, delta was the ratio of the z term to xx plus yy. We figure out how to map it. Here again is a Floquet dynamics. Don't worry about that part of it, but eventually there is by changing phi and theta, you can get whatever value of delta you like, get this similar dynamics. So the diffusion, subdiffusion, and ballistic has been predicted for various values of delta, and we see it in the average behavior of these transfer magnetization. And then we had the probability distribution, so we can look at this variance, also follows the KPZ prediction and also follows many numerical work. So again, we are doing a little cheating again. And well, I mean, there's a place to go and verify. And is all consistent with the KPZ picture. Okay. But as you realize, we have these histograms, this probability distribution, which we can really carefully study because we have so much instances of the circuits. And I'd like to, before I show you the higher moments, I'd like to invite you to think about how many moments do you need to analyze? Okay, we are again cheating. Someone tells us that we have to look at higher moments. But you see, when you think about the universality class, how many moments of the distribution do you need to verify to say that this dynamic belongs to this class? What if it fails after moment 16 or so? So it's a rather unexplored question because, you know, numerically or theoretically is not very easy to get to skewness and kurtosis. So we are really making the claim usually before going and analyzing the higher moments. Here we had the chance to go and look at the higher moments, and the spoiler is that it doesn't match the prediction of the class. So this is the definition of a skewness and kurtosis, or rather excess kurtosis, and I'm about to show you what we got in here. So skewness as a function of various values of choices of mu, it gets closer and closer to 0. So it becomes very hard to analyze it. Originally, it seems to go asymptotic to a finite value, which is the prediction of the KPZ. So remember the ceiling picture I showed you, whatever ceiling you think we should go for, there would be a different prediction for the universality class and then consequently for the value of a skewness. They're up here, but this is keep going smaller and smaller, and it seems it's going to have longer and longer time to get there. So what would happen asymptotically when mu is very small and you have to write very long? So it's not easy to analyze with our data directly. But what we could do, we can collapse this data based on some heuristic and find a scaling function, a scaling factor which allows you to collapse. Now, the beauty of this finding this scaling is that these two non-commuting limits now appear on the two ends of the axis. So if I could have gone more and more, now I have to convince you that if I could have gone more and take the limit in this order, I would be in here. And if I take the limit in this order, I would be here. You can see that the cold atom group, in fact, consistently fall into this limit. But what I like to argue is that we have to be on the other limit for this conjecture. That's where you got to be. So the two times to infinity and mu to 0 non-commuting limits, the order of that you take them matters. And I think the correct order to take them is you take mu to 0 first and then times to infinity. So mu to 0 first, time to infinity, which brings you here. So which we get a value close to 0 experimentally. This is inconsistent with the KPZ conjecture, either this one or the other one. The other one probably is not using of it is not probably even justified. Okay. Our collaborators have also theoretical predictions and papers, so we are still, I agree with them. We can even verify them, verify these two theoretical proposals. Still, we agree with them, so we can go one step further, and we can measure at these excess kurtosis I mentioned. Now you can see that asymptotically, this value also seems to tend to 0, and it seems hard to argue that it would. We don't have collapse in here. It's hard to argue that it would just come and if you wait enough, it would jump into any of these predictions. So within our data, within this time frame that we work, we see that we disagree with the prediction of this nonlinear model. But still, we are consistent with these classical Landau-Lifshitz. So, but also I want to say that classical Landau-Lifshitz is a model which is written with minimum requirement to capture the physics, and rather the deeper problem, the deeper issue of why the scaling functions so much look like KPZ, but these moments don't follow the KPZ is still alive. So, as you can see, this is I want to be very clear, this is the work of many Googlers who work behind the scene, and I had the chance to be here, but the whole infrastructure put by Google is this great team in here. And we have been very fortunate in the last decade that we collaborated with many people in the academic side for these experiments and many other experiments, which I didn't have time to share. And you probably see your picture in here. If not, we can talk about it. Okay.
Questions?
So, I mean, so did you do both the domain wall and the stationary initial conditions? Like what you showed, it looked like the domain wall, is that right? Or you did both initial conditions for the current?
Domain wall is when mu is to infinity, right? You just make pure blue, pure yellow. Yes, we could do that. But the significant physics is where you go to these very small mu's, which become experimentally very hard.
Okay, but it's still a domain wall with a very small jump. Is that right? Or when
well,
mu is small?
Initially, you choose a mu. You tell mu is 0.3. And with that probability, you're going to decide if this guy is going to be blue or not. It's a mixed initial state. Well, it's a purest. Well, so you choose a mu value, and that mu value sets how initial states look like.
Okay, but it's homogeneous. Everywhere you choose.
No, it's not homogeneous. For every qubit, you flip the coin mu with that probability you decide.
Right, but there's no left half and right half, right? For every site, you do the same.
No, look, e to the mu gives the probability of blue. E to the mu gives the probability of yellow.
Okay.
So when you cross the middle line, this.
Okay, so on the right half, you choose with a different probability. That's a minus sign, I guess. Is that right?
No, it's not minus. I changed the color. I could have done that.
Oh,
yeah,
okay,
e to the minus
minus
mu gives the probability of blue on that side.
Okay, so it's always step initial condition, even for a small mu. It's only that the probability difference is smaller.
Yeah, right. Yeah.
Right.
But you really have to go to these very small mu's, which you see, you cannot even with eye see a contrast. Yeah.
Okay, but then you would expect tracy widom, right? Not bike grains.
Either way, it's hopeless. Either way, it fails. Either way, it doesn't. So let me see which one we should have done.
Okay, tracy widom is
right. We have to do bake grains, not tracy widom, because of the. So let me see. You have to, yeah, because mu goes to 0, you start with this one. But anyway, the other one also didn't help. The other one, well, okay, so look at the predictions of these two models, these two initial states. They are way out there.
Sorry, just one question about integrity breaking. So the point is that suppose you break integrity but preserve spin symmetry, these are expected to be relatively robust. So when you in the experiment, when you sort of suffer from breaking integrity, what kind of integrity breaking terms can happen? Like, can we have integrity breaking but symmetry preserving, or you also lose the symmetry?
But this is how we break it, and I can show you that the distribution of the energy levels go to Gaussian. Maybe I should that would be convincing. If I have it, I can find it.
In terms of the KPZ part of the talk, but for the KPZ
Okay,
part of the
sorry.
talk, there, when you have integrity breaking effects, is there an idea of what kind of terms?
Why does it integrability?
No, here it's fine, but suppose you actually have integrity breaking. In the realistic scenario, you might be breaking integrity, but the point is it possible that you're preserving symmetry but breaking integrity? Because there are results where if you preserve symmetry but break integrity, still KPZ physics can remain robust. So question is something like that possible to check, or?
Yes, but it didn't even survive in the absence of integrability breaking. The KP, well, fine, you go to higher moments, it didn't even survive this test.
Sure, but I'm talking about the first plots where you see the exponent. I mean, even that might.
So after this plot, we focus on the orange line, we focus on delta equals to 1, the Heisenberg point, and then we get disappointed because even at that point, KPZ is not applicable. So what more do I want? Sure, we can break integrability different ways, but even at the delta equals to 1, it's not standing the test, right? Our approach is to look at the higher moments, and probably you will find a stronger, I think we have numerical evidence. Away from delta equals to 1, you have a stronger, much better numerical, is more easier numerical showing you that the skewness and kurtosis are different from predicted value. You get a finite value of those, you get the wrong KPZ values of them much easier.
Orange, t power 0.63. This is at delta equal to 1, or what is?
Yeah, orange. Orange means is on that delta equals to 1 line.
So
yes.
that is KPZ, at least the exponent is KPZ, right?
Yeah, that's exponent is KPZ. You're
KPZ,
right.
so
super diffuse.
Right. So that exponent could survive. So that is a KPZ exponent. I mean, the skewness may not agree, but that is still a KPZ exponent, right? T power. Sure. So I was talking about the robustness of that exponent if you have integrity breaking terms.
Yeah.
So, okay.
That I don't. Okay, sorry. Yeah.
Any other questions? If not, let's thank Pedram once again.